Welcome to Walkabout the Galaxy, the evolving astronomy podcast where the science is universal, the opinions are personal, and the hosts are back in town.
Oh, yeah.
We are strange, charm, top and down the astroquarks, also known as Josh Caldwell,
Addie Dove,
Jim Cooney,
and Audrey Martin.
Coming to you from the Walkabout studio at the University of Central Florida. Subscribe to us on Facebook, Instagram, and YouTube. You can contact us at wtg@ucf.edu with questions, suggestions, and compliments. Our stumper today is inspired, of course, by Star Trek.
Oh, okay. Mm-hmm.
In the original series episode, All Our Yesterdays, do you guys remember this episode?
Yep.
I mean, once you describe it, I might.
The intrepid crew of the Enterprise is investigating the planet Sarpedon, something maybe. Anyway, the star is about to go nova, and for some reason they beam down to this planet, and they they discover a librarian, Mr. Ataz.
Okay.
Get it? Ataz.
A to
Z.
Yeah.
The librarian.
I love that.
Who tells them that they have to leave. It's very late. You need to go. So the inhabitants of this planet, knowing that their star is about to explode, they don't have space travel, but somehow they have time travel. So they go through the, whatever it's called, the Atavachron or whatever. They go back in time to their time period of choice to live out the rest of their lives, right? So that they avoid getting blown up when the star blows up by just living before that, right?
Okay.
So, and then there's all sorts of hijinks.
Why do I feel
with
like the
Spock.
star was not actually a white dwarf that could go nova?
Because that would not make it a habitable planet. That's why you think that.
Yeah. Well, what I'm saying is,
but that's not
novas
fun.
only happened at white dwarfs and binary systems, and I guarantee this wasn't that. But that maybe
Right.
they didn't know what novas were.
That's
back
not
then.
really fun.
Yeah.
so-
No, it's not fun. I'm sorry. Go
So
ahead.
your stumper is if you were in such a situation here on Earth, so you have our Earth history to go to, and you have to go back there, and that's where you're living for the rest of your life. Where do you go? Where, when? I'm gonna allow you to choose place and time, although I'm not
On
sure
the
that's
Earth?
how that. Yes, our actual Earth, our actual history. This is where you have to go
Jeez.
to avoid getting blown up.
I'm a fan of
or
the present
incinerated.
and future.
Yeah. I feel like we've had a similar question before.
We definitely have had
Okay.
similar questions, but I think they've usually been like, it's a temporary visit, like a day or a week or something like that.
Is it? Or are other people coming back with me?
You can, I mean, that's up to you and them to work out.
All right. If I can bring more people and we all are happy about this decision, I would go back to at least
so
like.
the situation is the Earth is going to get incinerated by the
Yeah.
sun blowing up.
But we have time travel.
Where do you? But
we
you
have
have
time
time travel back to our past. Where do you go?
Dinosaurs.
Really?
Yeah. Dinosaurs.
Oh man, she stole
I'm
my
not
answer.
gonna be specific about it though.
You could pick a different. There's lots of dinosaur
There's lots of
times.
You're
dinosaurs.
going back
I'll-
67 million years ago or something like that.
Yeah,
Peak
yeah.
dinosaur.
Peak dinosaur.
Yeah.
Really?
I was also going Mesozoic.
Yeah.
Really?
Oh, wow.
Yeah.
I mean,
That's
there's got to be a lot of cool
A
things.
bold choice.
I just
Well,
don't ever.
because
I
you
don't
know
want
who
to be
sucks?
like burned at the stake for being a
Humans?
witch or something.
Humans. Humans have always sucked. We're always violent, and we hate each other, and it's always awful
And
so-
unpredictable.
and very unpredictable.
You
But
know
go
what
back
else
to the
is
dinosaurs.
unpredictable and violent?
Dinosaurs.
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 Or
Well,
maybe they're predictably violent.
I don't know. But it's good. It'd be cool. Maybe the life wouldn't last long. Maybe we get munched, but there's no better way to go than getting munched by a dinosaur.
I know.
I
And then maybe that dinosaur gets preserved in some swamp,
Yes.
and then future people
are like,
find
Find them
human.
in the
No, it
but
won't.
they
They won't know
didn't,
it's a
because
human.
that would have already happened.
Yeah.
right?
How does this time?
I don't know
paradox thing
how.
work?
I don't know how that works in
Yeah.
real life.
Because the sun is about to blow up now. So have your bones been discovered in a dinosaur fossil yet?
maybe
No,
in the
because
Not in this
parallel
timeline.
universe.
This timeline,
This is
yeah.
the timeline.
But it's, I don't understand how.
Yeah.
No.
All right, where are you going, Addie? I'm definitely not. You know what happened with me if I went back to the dinosaurs?
What's that?
I would starve to death.
Oh.
But you're a vegan.
I mean, I would maybe relax some of my restrictions there, and then I would starve to death.
Yeah, I'd probably die pretty quick. I have bad allergies.
You'd just be like roaming around, sneezing. Shh, there's a T-Rex coming.
Yeah.
Like, achoo.
Choo!
I don't know.
No? you're punting. You're like
gonna
not
punt.
interested in this one.
What about like the scientific revolution? Like when coffee first came to the UK and they were like, we don't have to be drunk on wine anymore.
Yeah.
Yeah, I don't
What
know.
about the 60s?
I would love to
Woodstock.
go to a lot of these places because I think it would be cool to experience them, but like to visit. Like if you're if you're gonna live out your days there,
Yeah.
it's a big commitment. And like I like a lot of our technology things.
Yeah, I know.
And you
Although
wouldn't.
I used to want to live in like the prairie days.
So you're just
maybe
going to stay
I'll-
here and get incinerated?
No, I'll move back to like
Prairies.
prairie days. And,
Prairie
like,
days.
That's a good one.
Laura Ingalls
Little house on the
Wilder.
prairie.
Ooh, I'm gonna move to like Prince Edward Island from Anne of Green Gables,
Yeah.
and
Nice.
but in like the early 1900s.
Yeah, it's tough. I mean, the people thing is definitely a fair point. So that would be a tough, it's like trying to think of it like a war-free time.
Yeah, it's tough,
Yeah,
right?
it's real hard to do.
That's pretty impossible.
I mean, you could go to a place where it was less inhabited. Like you could go to North Florida when there was. I was trying to think of a time, and like there's
You
people
should
in
never go to North
for a long time. Maybe back in the day it wasn't as bad.
Without air conditioning?
Well, I would go during a Maunder minimum
Oh.
or glaciation. Ooh, yeah, like the Earth when the U.S. was glaciated or something. That would be cool.
But no one would go back to try to help save humanity, or
by what?
By stopping
changing
the sun
star?
from
no,
exploding.
by like moving the people to a different place.
Oh,
You can take your brain back in time and be like, we can go to Mars.
build giant spaceships.
I'm just
Maybe that's what Elon Musk is up to.
I'm just saying
Maybe
I'm
he's from
not
100
doing
years in the
that.
future.
Maybe he's planning on going
this-
back 100 years once he builds his spaceships.
Yeah. Well, just a random trivia. That episode was written by a fan of the show.
Of this show? Not yet.
A fan of Star Trek, had no other writing experience. She wrote 2 episodes of the original series. That one, which actually was the next to last episode of the original series, Star
wow.
Trek. And the other episode she was called "Is There in Truth No Beauty?" Her name was Jean Lizette Arrest or Aresti. I'm not sure how to pronounce her last name.
Okay.
She was a librarian
Oh.
at UCLA.
Nice. Nerd.
So today we'll talk about donuts, dark matter, and deuterons. But first, this episode of Walkabout the Galaxy is brought to you by the Conduction Band. Get your groove on and your electrons moving with the Conduction Band. Hanging out just above the Fermi level, the Conduction Band is ready to strike up a tune of your choosing. For a little bit of energy, get your music current and your current flowing with the Conduction Band. Featuring multiple states and ready to make your semiconductors sing, the Conduction Band is just what you need for all of your solid-state devices, from solar photovoltaics to cell phones and more. The Conduction Band. Leap ahead.
Leap ahead. The leap to conclusions, Matt. It's from Office Space.
Oh,
Frog tape, like painter's tape, but it's green.
Oh, I like it.
interesting.
Leapfrog.
Honey bee.
Jim gets that sort of by default. Intel.
Oh, okay.
They have a lot of.
But did you mean
they have a
Honeybee the
lot of-
company or Honeybee the bee?
There's lots of. Yeah,
company.
they probably do.
I like the bee
Lots
too.
of these have different slogans.
Okay.
Space news.
Space news. There were some actual news articles about some concerns that have been raised by folks in the Florida area, by ULA and Blue Origin. There was a letter that was written
By
I heard
who?
about this.
by
Citizens?
ULA and Blue Origin. Wrote the letter.
Oh.
These people from those companies wrote the letter.
Okay.
With concerns about SpaceX.
Who
and
wrote the? I'm just kidding.
I tell you
Audrey?
what, your
You almost
expression
had me
there,
there.
really, you sold it.
I used to be a professional actress, so
Used to be. But against SpaceX for their Starship Heavy launches from the Cape. So there's a lot of sorry, not Heavy. The Starship.
The big, the new one.
The big one.
Super heavy.
Because there's super heavy. Because there's a lot of concerns about damage to infrastructure in the area.
well,
And environmental concerns that these other companies are like, we need to, if you're going to let them launch there, you need to limit the number of launches they can do from there per year, or just let them launch out of Texas. Like, why do they have to come to Florida to do it?
So they are planning to launch this giant rocket from Florida as well as Texas. Is there a particular reason? Do they need 2 launch sites, or is there some benefit to having?
I don't remember. There were a bunch of environmental studies done about launching here, and they sort of had mixed conclusions. I remember when those came out.
Okay.
Who did those studies?
Other companies, like some firm, I think.
The firm that does environmental studies.
Cool.
Yeah.
Are they concerned about if it crashes or something, if it blows up, or if it just from the normal launches?
So when they do that stuff, they consider like the normal launches, but they also consider like what would happen if it blows up.
Okay.
And
both.
that's less of the
That's fair.
environmental study. That's more of the like
Infrastructure.
disaster
So are
mitigation
they
type
worried
things.
that if it blows up, it would also take out the like ULA and
Yeah.
Blue Origin?
Stuff.
Whoa.
It's a lot
super
of
heavy.
energy,
That's fair.
stored energy.
Too
Yeah.
untested, too dangerous, and too potentially disruptive for the spaceport.
They're a ways away from being ready to launch from here, though. Like, they don't even have a launch. They're not even building a launch infrastructure yet, are they?
They've
here?
been looking at the assessment is they've looked at like which pads. Because they are talking about launching up to 44 times a year from pad 39A.
44 times a year?
Yeah.
This is
For the big giant one.
this is the one that's currently being tested.
Yeah.
And then will be tested with the chopsticks.
Yeah.
44 times a year.
Yeah.
My goodness.
I mean, Falcon 9 launches hundreds of
I
times
know.
a year now.
Yeah,
right?
I guess that's
Or
true.
over 100.
Over
anyway.
100, yeah. And then potentially building a second pad also out there.
Yeah.
Like,
Well, yeah, interesting. Well, we're still waiting for their 5th launch ever, which will take place from their so-called starbase in Boca Chica, Texas. This one should be exciting, assuming it happens, because of the potential use of the chopsticks
I know.
to capture the main booster
Yeah.
when it returns. So it actually sort of stuck the landing on Flight Test 4. It came down at the spot in the ocean where it was supposed to, at least approximately. We know this because they had a buoy anchored there with cameras that saw it come down and sink into the ocean. So it was like at about the right spot. But that whole chopstick thing seems kind of remarkable. So I'm excited to see that happen.
It's not like I can think of a better way to do it, but I feel like there is a better way to do it.
I think they're doing it the better way. I think they
Really?
have.
You think
yes.
chopsticks is like the most...
No, the way they've been landing everything else,
Yeah.
which is on a big open space where you don't actually have to be exactly on the bullseye.
Yeah.
And if you're not exactly on the bullseye, you don't land on...
You don't destroy your launch structure.
Yeah.
Right. So that's seems like the better way. And the only I don't know why they're not doing that with this, but presumably it's just about legs. I can't think of any other
They like,
reason.
just don't have legs.
Yeah, I mean, the
their
Falcon
thing.
9 boosters, when they come back, they deploy legs.
Well,
so
why
that when
can't
they-
it have legs?
I mean, I don't know. That's an
How
excellent
much do you want to
question.
bet it was Elon eating some rice? He was out for sushi, and he was like, you know
like,
what?
What about, or he was watching, I still think you're watching like Karate Kid or something.
Oh, sure.
yeah.
Yeah. Yeah.
Sure, with the fly
Yeah.
with his chopsticks.
Yeah,
It's like, that's
I don't
brilliant.
know. So
Brilliant.
certainly, Anyway, we'll see what happens.
There's a non-update on Starliner, which is the Boeing one that's still up on Space Station.
Right.
The non-update is it's still up on Space Station.
Right.
We haven't had any updates in a while.
But there will be an update tomorrow as we're recording this. So on July 10th,
Probably by the time this airs, there will be an update.
there will be an update. And as you pointed out last time, they're not at all, don't use the S word.
Yes, they're not streamed.
The reason that they're staying up there is because there are tests that they can do only while they're up there, and they can't do them after they come back. So
Like, it's not like everything's perfect. They're
Right.
obviously doing this to understand what the issues are.
Right.
But they're not stranded. They could come
Right.
back at any point.
right.
Are they going to come back using...
Sure.
They will come back on Starliner.
Okay.
Yeah.
Well, then that's fine.
Right.
I mean,
it's all
it's-
hunky dory.
I'm not going to be an astronaut for this very reason, and also a lot of other reasons, but this is definitely one of them.
Yeah.
But
Getting
like,
stranded in space.
yeah, but like they signed up for this. This is a part
They're
of,
good.
They're
They're going to
fine.
have a nice ride home, and they're getting extra bonus days up on the space station.
Yeah.
So,
Yeah.
Imagine the overtime.
yeah. So we've got a couple of short sort of
Shorts.
space physics news.
Yeah.
We could maybe categorize. Why don't we start with those?
Did you get on a scale lately? Top quark.
Top quark.
Yes. It's been difficult to figure out just how big top quark is.
It is. It is. I do refuse to get on a scale because...
There's a new result from CERN estimating the top quark's mass.
Top quark mass.
And it's the most precise value to date. So previously estimates were between 151 and 197.
Which is correct.
Totally reasonable number.
Totally correct.
Units of mass.
Yeah, some units.
But so a new measurement using the Large Hadron Collider, LHC.
Is that the right?
It is. That was the correct pronunciation.
Okay,
yes.
What's
have
the
most
incorrect?
Precise.
Hadron.
Oh,
That's Josh's pronunciation. Yeah.
I don't like hadron.
No,
Sorry.
none of us do.
172.52 plus or minus 0.33. My scale doesn't get that precise.
So
That's pretty
let's
accurate.
put this in some kind of context.
And the actual units are giga electron volts per c squared.
Right.
So what's something else that has a mass in those units that we're kind of like have some familiarity? So
That's a good question.
what's the most massive quark? The bottom quark?
I think it's the top quark.
It is the top quark.
It is the top quark. Yes.
Okay. And what's a proton?
Right. Much less than that.
What's a proton made
Top
of?
quark is 184
on,
times
Jim.
the mass
Top
of a
quark
proton.
is what is it? 2 ups and a down, or 2 downs and an up?
Okay, it's ups and downs.
Ups and downs.
Ups
Is
and
there
downs.
anything that we're familiar with that's made of tops?
No. Those top and bottom quarks, as well as strange and charm quarks, don't
That's us.
regularly exist in nature.
That's true. We are quite unique.
Yeah, we don't regularly exist. Up and down, they're all over the place.
I know.
Okay.
But like, what's an electron? What's the mass of an electron?
Less than that.
It's about 1/2000th of the mass of a proton.
What did you say the mass of a proton was?
I did not say what the mass of a
Mass
proton
of a mass of an electron in MeV
Right.
per c squared is 0.5.
So
0.5 MeV, and a top quark is
is.
it's
172
something
giga.
EV, right? And that's
So
billion
170
instead of million, right?
So it's 170,000 in the unit that an electron is a half.
Yeah.
Right.
Okay.
Jeepers
So,
creepers.
Pretty heavy.
pretty heavy.
That's a couple hundred times the mass of a proton, sounds like. Ballpark.
Yeah.
Or 100 times.
184 times the mass of a proton.
Oh, okay.
Yeah.
Yeah. Did you already say that? Okay.
Yes.
Nice.
So,
well, it's
right,
who
so-
cares? Who cares is the question.
I care. I mean, that's interesting.
No, it is. I mean, it's
Because
important.
that's as massive as like a very, very massive atomic nucleus.
Yeah.
Yeah.
Oh yeah. Wait a minute.
And knowing that, Matt, I mean, it helps. So we have this standard model of here are all the fundamental particles that exist, but the more we know about the precise masses of all the pieces of that model, the better predictions we can make about interactions between the various parts of the model, and so you can predict what should happen when you crash things together more accurately, which allows you to better test the standard model. So you know all the parameters, then you can test everything better. So
Yeah, there's always these questions when we're trying to measure other things, like trying to figure out other properties of other particles, and like the Higgs boson.
right,
It's like
right.
so much
You want to know more
unknown.
about that? Know more about the top
Know more
quark?
about the ones we do sort of know about.
Yep.
Yeah.
Yep.
When was the top quark discovered?
It's a good question. Don't know.
1985.
Correct.
19 which what 5?
9.
9-5. That's
Really?
recent.
So recent.
Yeah.
So recent.
Not even 30 years.
Younger than
It's younger than the actual top quark.
the actual top quark. It's younger than most of the quarks.
Yeah. All right. What's our other
yeah,
space physicsy news?
Deuterons.
I'm so excited.
Deuterons.
Deuterons.
Stretch. It's a stretch.
Yeah, Riley likes that joke.
Deuteron. No, she'll love it.
Deuter.
Deuterons. What's a deuteron?
Is it in the Big Lebowski?
I know there's a book
Not
about it in the Bible.
Deuteron.
Deuteronomy.
Deuteronomy. Yeah.
Deuteronomy.
It's just a.
I know. Well,
a
Deuteronomy.
heavy ion, heavy
Deuteronomy,
hydrogen.
Deuteronomy. Just to be serious for a second, it's the study of Deuterons.
Yeah.
Deuteronomy,
Deuteronomy.
like astronomy.
yeah. Study of Deuterons.
stars.
Is it?
That's
is now.
not true.
That's what that whole book is about.
It's a physics book.
Physics book. Deuterons are heavy hydrogen ions.
Right. So it's just a proton and a neutron stuck together. It's the nucleus of deuterium.
Yes.
as a deuteron.
What's its mass?
Well, about twice the mass of a proton.
Okay.
But not exactly.
Okay.
So the news about them is they are some component of cosmic rays. And cosmic rays, they're not rays, but very high energy particles from out there. Most
beyond
of those
the
things
galaxy,
beyond the galaxy,
usually.
yeah. A lot of times they're just protons. The majority of them are just protons. Sometimes they're positrons, things like that. But sometimes they're deuterons. And we have a detector up on the International Space Station where our friends from that aren't stranded, that are not stranded, are.
Not stranded friends.
That has been looking at these cosmic rays for years now. It was like 2011 or something like that. AMS, which stands for what?
Alpha magnetic spectrometer.
Right, to looking at these cosmic rays. And it's been detecting not only that they're incoming, but what they are, protons versus deuterons or whatever. And it's found that there are far more deuterons than there should be.
Okay, so I have so many questions.
I have very few answers.
How do they figure out what the cosmic ray is made of? So you have some kind of particle detector. You have this very tiny particle, a proton or a deuteron, say, that's been accelerated in some distant galaxy and has made its way across the cosmos, and it hits something that can detect that. How do you know? I assume they're basically doing like mass spectroscopy.
I was thinking either mass or like energy.
Spectrometer.
They have an electric
Oh,
field.
They probably, it's probably measuring like
how much it like
mass to charge ratio or something like that, and that would tell you
whether it's
just a proton or a proton with a neutron.
Right. Okay. And so that's the first question. The second question is, why would we have any expectation about the composition of cosmic rays?
Well, so we try to have these models for where these things could possibly come from. Like, these things are coming in at insane velocities typically. And so we have to ask ourselves, okay, what kinds of things in the universe could produce deuterons, for one, and then what kinds of things could accelerate deuterons to the crazy speeds that we're see these things coming in? We know that deuterons were produced in the very early universe, right? I mean, so there was a very brief period in the very early universe where after you only had protons and neutrons and before you had helium, there was a period of time where you could make deuterons. So if you stick two deuterons together, you can make a helium, right?
Okay.
Two duties together make a...
I was really expecting a joke there, Jim.
I don't want to get censored off the show.
Well, too late.
Too late. I know. This is my last in-person show. This is very upsetting. Anyway, so you can make helium. But before you made helium, there were some deuterons. So it was like 10 minutes in the early universe or something like that when there was a sea of those things. Some of them remained after once you started to make helium. So anyway, our models predict roughly how much of that stuff there should be in the universe. And if you just take those and accelerate them by whatever means you possibly can, there just wouldn't be enough. You wouldn't see nearly as many as we actually see in our...
Okay.
So there must be other ways of making...
The fraction...
that can't be the only source of deuterons.
Right. But it's not that easy to make deuterons. I mean, you can take a helium or something and smash it, but that's not that easy, right?
You don't get deuterons in a supernova?
So you do, but not in the numbers that we would, if...
You deuteron.
They're thought to overwhelmingly originate from interactions within the ISM, the interstellar medium.
Really?
And helium.
Oh.
Right.
Yeah,
So you can...
Not from supernovae.
Huh.
Is it too energetic in a supernovae?
Well,
in a supernova?
How do you make a deuteron in the interstellar medium?
I'm just reading the background of the article. I don't know yet.
I think you take a helium and you fly it through the interstellar medium and crash it into something else, and it splits.
Yeah. The helium is basically two deuterons stuck together.
Right.
What you just said.
Right. It is, but they're pretty hardy stuck together. So anyway, the number of deuterons that you should make. Yeah. It's hard to fission a helium. You can do it if you have enough energies, but when we calculate how much deuteron you should get from that process and from the early universe and whatever, it's not as much as we actually see.
Does anybody have any answers?
No,
to this
I saw no answers whatsoever. It's just it's an open mystery. Now go, listeners, find out where the hell the deuteron is coming from.
But how much more? Like, is it? You said like a lot more.
Oh, I think it's a lot more. Yeah, that's a good question.
50% more? Is it like 500% more?
I think it's a lot more, like more than 100% more. Yeah, I think it's something like that. But that's a good question that I don't have the answer to.
Okay,
thank you.
Cool. Well, somebody out there can get
Figure
their
it out.
PhD and have a career figuring
Absolutely.
out why there are so many deuterons in our cosmic ray population.
Yeah.
I have to say the author list on this article is like a whole page long.
Wow.
Oh yeah.
Well, it's because it's CERN.
yeah.
So
No, this is the one.
This
that's
is the
like
AMS.
It's
But
on
this
the
is-
space station, but
this
it's
is
like
just
an
modern
so.
science, right?
Yeah.
All these
Yeah.
big experiments have so many people working on them.
Takes a lot.
AMS is like this big giant funded experiment that's
Right.
been going for, like you said,
Yeah.
over a decade. And
Yeah.
Yeah. Okay, cool. Well, before we talk about the protoplanetary disk, let's do our trivia. So I was looking at Jim like he had the trivia, but he doesn't.
I don't. No.
Our sponsor
I have
today,
the answer to the trivia.
Our sponsor today, as you know, had to do with semiconductors. And one of the applications for semiconductors are solar photovoltaic cells.
okay.
Our trivia is about the history and evolution of photovoltaic cells. So here's a few questions for you to ponder while we
Okay.
talk about how planets were formed. When was the first photovoltaic cell created? When was the first practical solar photovoltaic cell created? So that you could like put the thing in sunlight and
Actually produce
get some
electricity.
electricity that you could do something with from, rather than like a laboratory experiment where you see I shine light on something and I see a little current, which was the first question. What was the efficiency of that first practical solar cell? In other words, what percentage of the sunlight incident on it got converted to electrical energy? And what is the current world record for efficiency of a solar cell? So those are your questions, all about solar cells
Cool.
today. Okay?
Great.
Okay.
Definitely going to know the answers to this.
You could.
I feel like that
feel like
last
I
one
have
is
a
one that
magnitude.
we should know the answer
You're going to
to.
get close to anyway.
But that
Yeah. You won't be off.
We're
by
gonna
an order
show
of
our
magnitude,
ignorance, but
I
yeah.
hope.
5,000%.
Maybe so. Could be surprised.
yeah, that will be surprising.
Okay, so for our next topic, we have donuts. I
delicious.
promised at the intro.
Yeah.
Delicious.
Okay. So there are apparently a variety of different models for how the.
I love how you say apparently here.
Well, yeah.
It's like
You're going to
there
learn all
are
about this soon when you teach astronomy.
I know. I know. I'm gonna have to learn a lot.
apparently there are these things called asteroids.
So there's this, and then sometimes they make a meteorite. But okay, so in the protoplanetary disk, before planets were formed in the solar system, there are different geometries that are hypothesized. So was it just a flat frisbee, totally homogeneous? Probably not. It could possibly have been concentric rings of material that later formed planets. These individual concentric rings.
Yeah. So part of this is we have observations now, especially
Yeah.
over the last decade or whatever, of protoplanetary disks. So for a long time, we've had theories about how it can form and shaped. And sometimes, it's like sort of one thickness all throughout. Most of the models now have it being pretty thin in the middle and then sort of
Flaring out.
flaring out on the edges of the disk. Because it's easier, because that fits physics better.
Yeah.
But then also, they evolve over time, over the lifetime of the disk.
Right.
And usually those circles happen because you have a planet forming that opens a gap in the disk.
Yes. So what these researchers found by looking at an iron meteorite, which I think is a pretty unlikely source for understanding the protoplanetary disk, because an iron meteorite requires pretty hardcore differentiation within an asteroid, thereby getting rid of a lot of the information within the protoplanetary disk. But so their study basically.
So I like how you introduced their conclusions with
weird.
by the way, I don't really see how they could possibly get their
No, I mean, I
conclusions from
think
how
that
they
I
did it.
can see how they got their conclusions. It's just an unlikely source.
Okay, all right.
But so they're
Surprising.
It's surprising. Yeah, surprising. Also,
Delightfully surprising.
yeah, I feel like those are synonyms.
Go ahead.
So they're in favor of a donut-shaped protoplanetary.
All right. So let me just
this,
go.
yeah.
let me
But
just,
at what stage?
That's a great. I don't know the answer to that.
so
Okay, yeah.
just to set. So just to
the stage.
encapsulate
Yeah.
things. Some people looked at a chunk of iron that came from, as you were describing. Okay,
Multiple chunks of
many iron meteorites.
Yeah.
And the iron meteorites, as you said, must have come from the center of a largish asteroid, big enough so that it was warm enough so that the metal sucked to the center, sunk to the center.
Yeah.
Then this thing got broken apart.
Yeah,
and then a piece of that metal ended up landing on Earth.
Correct.
And then they looked at it and they said, you know what? I can't see how we could possibly have gotten this unless the original solar system was shaped like a donut.
Correct.
Okay.
Yeah.
Makes sense.
Yeah.
I got it.
Yeah. So what they found when they were looking they found a lot of refractory metals within the iron meteorite. And in particular, they found iridium and they found platinum, which are two metals that pretty much exclusively were condensing out in the outer solar system. And by outer solar system, here we're talking about beyond Jupiter-ish. So in the teens, AU, like somewhere in the like maybe 10s to 20s, which is weird because for the asteroid, for this asteroid that's differentiating to be hot enough, it's expected that it should be in the inner solar system because it would need to be warm.
Right.
But it wasn't. And so the idea is that there was this disk beyond Jupiter. So as Jupiter was forming, there is a disk or a donut.
Okay.
Yeah.
So they're seeing
had to
metals.
have been transported out to the outer disk when they were still like molten or at least still really hot. They had to have been gotten out to the outer disk to form these things. So it has to be a continuous disk as opposed to gaps.
It rules out the
sort
gaps.
of concentric rings with gaps business.
And then after the asteroid differentiated, made a core, all of that good stuff, it then collided with something else and was brought inward and then subsequently landed on Earth. Okay.
It's amazing how you find clues in unexpected places.
I know, it's really fun. I think it's really cool, and I've never like looked too much at iron meteorites, and I think maybe I will.
Maybe you need to take another look at them.
Maybe I should take another look at them.
Yeah, I mean, a lot of times when we think about when we talk about like where different asteroids form and like what materials they're composed of and where they have to form in the solar system, like what you look at and what a lot of people look at, is the things that are gonna maybe only exist in the outer solar system because it's cold, right? So more volatile things. Yeah. But this is looking at things like the calcium aluminum inclusions and other sort of metals that are gonna form at different places throughout the solar system too.
Yeah. Okay. Interesting. I mean, as I think Addie and Jim were both saying, there's an evolution of the shape. I mean, we've got pictures, as you were pointing out, of other protoplanetary disks, and at some point they are ring-like.
Yeah.
I think there's like a variety of shapes. Do they all end up as rings at some point?
At some point they end up as planetary systems.
Well, sure, yeah. Oh, you're saying multiple rings, not a single ring.
Right.
Yeah.
And there's always an exclusion zone at the very center where stuff is blown out. So you have a sort of a gap right around the star where there's not a lot of material. The stuff coming in gets vaporized and ionized and blown away. So there's this sort of like gap at the inner edge of the disk. And then all sorts of complicated things going on out in the disk. When planets are formed, they can open up gaps, but this was all happening before that.
Yes.
Yeah, so I think one of the things about it is it probably helps constrain the timing of when you get gaps and stuff like that forming. So these CAIs and these in these iron meteorites had to have formed like very early in the solar system before these other processes happened.
Yeah.
So
but it would have had to have been
timing
around the time of Jupiter, because Jupiter forming is a part of the hypothesis.
Once Jupiter forms, you
have to open a gap.
Yes.
Yeah.
So it had to have been before Jupiter formed. Yeah.
Unless these kinds of things always make me wonder, like how well we understand, like the chemistry and like these models are based on, I understand where this could condense or that could condense, and I always wonder how well we know that.
I mean, there's a whole field called cosmochemistry.
I know, but that's it's an active, ongoing, evolving field. This is just it's just like this all this cosmology stuff where JWST keeps showing us all these weird things in the very early universe, and we're like, but it may just be we don't understand galaxy formation well. It's not like all of cosmology has to go away.
Right.
This could be like maybe we just have to understand our cosmochemistry a little bit better.
Yeah, totally.
Well, one of the things that Audrey will be teaching her intro astronomy students next semester is the so-called snow line or frost line or ice line. You get to choose whichever you want to call it. That's one of the nice things about being the teacher.
I'll just use them all and confuse everyone.
Which is sort of the distance. It's used in the period of planet formation to talk about the distance beyond which the temperatures in that protoplanetary disk were low enough so that water could condense into solids. And because H and O, the constituents of water, are very abundant elements, there was a lot of water in a lot of mass that you can get there. You can't condense hydrogen or helium, but you can condense water and make solids so that you can make cores of big planets like Jupiter and Saturn and Uranus and Neptune and all of their big icy moons and all that stuff. So that's the sort of 101 story of like why there are big planets in the outer solar system. Is cooler.
Right.
So when I was a kid, there was the snow line and it was at whatever, 3 AU or something, 3 times as far from the sun as the Earth. But part of this whole story, what we were just talking about, is now we know that moved around during the whole planet formation time. There were times when it was closer to the sun and times when it was farther from the sun, not just depending on what the sun was doing, but also depending upon what the disk itself was doing and how much solar energy is penetrating the disk or how opaque the disk is to all of that. So I think this story about the iridium and the platinum and these iron meteorites moving around sort of is part of that dynamic picture of what that protoplanetary disk was doing. And as you were saying, it's not like throw everything out. It's just a little bit. It's a more complicated story about how planetary systems form. So
beautiful.
Thank you.
Now I need a Krispy Kreme.
Yeah.
Oh, I ate the last one.
Ah, son of a gun.
Ever?
Sorry.
Yep. There was a box.
There's no more Krispy Kremes.
When was the first photovoltaic cell created?
1937.
I was going to say 1935. I'll still say it, 1935.
Okay.
We're going to be way
1912.
Okay, so you're all wrong.
Perfect.
And I'm going to give you a sort
Are
of
we wrong
second
by
crack
like a century?
Yeah. Because
2027.
this is like shining light on something and noticing a current.
Oh.
So this is like shining a light in some electrodes or in a thing, and then when you turn the light on, there's a change in the current.
1756.
1803.
1818.
Audrey gets it this time. 1839, at the age of 19.
Oh, you should have gone with 1837.
Oh, yeah, you should have.
The age of 19?
At the age of 19, this is directly from Wikipedia, experimenting in his father's laboratory, Becquerel, whose name
Henri Becquerel,
created the world's first photovoltaic cell.
Wow. Okay. That we know of.
Yes.
Okay.
Once the electrodes were illuminated, voltage and current were generated. The photovoltaic effect has sometimes been called the Becquerel effect.
Oh,
interesting. Right. When was the first practical solar cell invented? And this is probably more along the lines of what you guys were thinking of, but practical.
Does practicality include like a battery, or does it just include like it worked outside?
What it means is there was a thing that you could shine sunlight on, and you could have a couple of wires coming off it, and you could, hook a little light bulb up to it, and that light bulb would turn on.
All right. 1935.
1912.
1923.
Audrey gets it again.
Dominating.
On April 25th, 1954,
I should have gone 37.
Yeah.
Bell Labs announces the invention of the first practical silicon solar cell. The New York Times forecasts that solar cells will eventually lead to a source of, quote, limitless energy of the sun.
You'd think.
We're still forecasting that, but we're closer to it now than we
It's
were
not
in
limitless because
1954.
it takes the energy from. I'm just kidding. Remember that?
We're 70 years away from that, but we've made some significant progress. So your last two questions are: what was the efficiency of that solar cell? How much of the
3.
How much of the sunlight? What percentage of the sunlight was converted into electricity? And what is our current world record for energy efficiency of a solar cell?
0.5%.
The first one, 0.5%.
Yeah.
3%.
3%.
I split the difference. 2.15%.
Addie gets this, and that does not split the difference.
I mean, it's in between.
It's
It is in between. but
It splits it, just not in half.
Yes.
Yeah,
Okay.
you never said
What
half.
was it?
6%.
Oh, okay.
6%.
Oh, pretty good.
Yeah. What is the current world record for efficiency of a solar cell?
Like 15?
79.
32.
Jim has it. 32.5%.
Wow, you really got it.
Yeah.
Nice.
For something
We
called a
each got one.
tandem solar cell. So the problem
Like a
is
tandem bike.
kind of
Okay.
there's multiple different kinds of semiconductors, each
Imagining
one
like
able
electrons on a
to
bicycle.
convert different wavelengths of light into electricity, because the problem is
Oh, that's smart.
you need a certain wavelength to like move the electron, and if your photon happens to be more energetic than that,
It's just
it's wasted.
Wasted photons.
So you need to
many
have
wasted
those things
photons.
going on. So 30%, I don't know, I think home solar cells now are in the high, sort of mid 20s for efficiency.
I wish it was so much
We're
more
probably not
efficient.
going to get much more than that.
Really?
Yeah.
This is something that
Yeah.
that naively, very naively, I was like, that's ridiculous. We should be able to be doing so much better than that.
Yeah.
Like, there's so much energy. Like, it should be 70, 80, 90%.
what I
I say that's naive because it obviously is. We were obviously nowhere near that and not going to get there.
Right, but also that's not really the problem. Like the reason that we don't like powering everything from solar cells isn't because they're only converting 1/4 of the sunlight. It's just not a problem to make 4 times as many solar cells.
Right.
That's not the limiting factor on things.
Right.
Okay.
What material
Anyway,
was
it'll all be
Becquerel's
moot when
sensor
fusion
made
is-
out of?
Ah,
Oh, that's
amazingly, I have the answer to that written down. Silver chloride or silver bromide was
Sounds
used
safe.
to coat platinum electrodes.
Oh, interesting.
And when the electrodes were illuminated, voltage and current were generated.
Cool.
Oh. Well, that's fun.
So
Go
a
on
little,
with yourself, Henri
galvanometer
Becquerel.
hooked up or something,
Yeah.
and you could see a little deflection of the needle when he turned the light on. So,
Fun.
yeah. While it may have felt like waiting to return from the International Space Station, it was just another episode of Walkabout the Galaxy.
Give us 5 stars and we'll give you the universe.
Be sure to follow us on Facebook and Instagram to get all our updates.
Subscribe to our YouTube channel and catch up on old episodes wherever you get your podcasts.
Our theme music was composed by Richard Jerusik. Production assistance is provided by Logan Basinger.
Thanks to our listeners right here in Central Florida, the best place for quarks to be,
Yay!
and around the world. Stay safe. I'm Josh Caldwell.
I'm Addie Dove.
I'm Jim Cooney.
And I'm Audrey Martin.
We're the AstroQuarks signing off until the next episode of Walkabout the Galaxy.